Welcome to our talk today about our escaping atmosphere. I thought it was fitting that we have a really windy day because we're going to hear about the other wind, the evil wind, the solar wind. But our escaping atmosphere, I was like, who knew? Who knew it was escaping? Where's it going? Why is it escaping? And is it going to be dangerous? Well, we've been assured that we have, although we lose tons of it every day, we have billions left. And so when we have our talk a billion years from now and we have our speaker back, we'll still be able to breathe.
The library will still be here.
We will still be here, of course, yes. And our computers will finally work. Maybe, but we'll have Windows 3 million and it'll be slow starting. I'm Stephanie Marcus from the Science, Technology, and Business Division, and I don't know what I'm going to say. I think I just said it. Today we have Douglas Rowland, and he is a research scientist at NASA Goddard. And because you people were asking about ionosphere, we're going to hear about the ionosphere. He is the chief of the Ionosphere, Thermosphere, Mesosphere Physics Laboratory. Is that still correct?
That's correct.
Yes.
Brandon.
He is all the spheres. And that is in the Heliophysics Science Division. He got his doctorate at the University of Minnesota, where he probably learned some of the Norwegian that gets him by when he makes his many trips to Norway, like Skull, right? And let's see. He's going to take us to the northernmost town in the world, where the atmosphere is thin, we don't have that magnetic protection, and my colleagues have wanted me to say it is rocket science because he launches rockets and they have cameras on them. We're going to hear all about that. So we're going to have a travelogue also to the land of fjords and auroras, and we want to say velkommen to Dr. Rowland.
Tusen tak, Stephanie. I thank you for inviting me to this beautiful facility and getting a chance to talk to you about this work. And thanks also to Davin and Danita and Michelle for helping me. Really appreciate it today. So I haven't been to the Library of Congress since 1985. I was 12, I think, and I really enjoyed it then, and I'm enjoying it today. So thank you again for inviting me. I want to tell you today about what Stephanie had talked about is how our atmosphere is escaping. And don't be alarmed, as Stephanie indicated, we have billions of years of atmosphere left. But the reason we study it is other planets, like Mars, they lost their atmosphere, most of their atmosphere. And so we want to study, it's a lot cheaper to study our atmosphere and try to extrapolate a little bit to other planets rather than to send all these probes to Mars all the time. So we use our natural backyard here as a way to understand Mars, other planets, exoplanets, and other solar systems. And that's why we're sort of doing this work. And as Stephanie mentioned, we go to a very unusual place to do this work because of the kind of unique geography of that location, the unique logistics of that location, and we use kind of a unique tool. If you're used to using NASA satellite data, like to map the weather or the wildfires or anything else, they're usually orbital satellites. They hang out for years up in space, and they take lots of pictures, and they beam them back down. We use a technique called sounding rockets, and these are suborbital rockets that go up, and they come back down, and they only are up for 5 or 10 minutes. The reason we do that is because they're very inexpensive. They're 1,000th the cost of a satellite. They're very agile. We can build them in 2 years and deploy them to remote locations and launch them. And we can target them. We can launch into very unique phenomena that might be hard to hit. Just if the satellite's just going around and around, it just gets what it gets. But if you want to get a specific target in the sky or a specific event, you might want to wait and pounce on it sort of at the right time. So that's why we use these sounding rockets, and you'll hear more about that later in the speech, in the seminar. I want to give some thanks to my team, and this is a partial image of my team. This is on the island of Svalbard, or Spitsbergen, in the archipelago of Svalbard. This is our rocket team that went to the field. In addition to this team, which is about 50 or 60 people, there's another 50 or 60 people in the back that are doing all the work, building the payload assemblies, building the instruments, analyzing the data when we get it back, doing all the engineering design work. But these are the guys who toughed it out for 10 weeks, some of them in frozen darkness with me, and we enjoyed it and really had a great time. And in addition to our team, there's also the sounding rocket office at Wallops Flight Facility. If you are on the eastern shore, just south of Ocean City, There's some great breweries down there, and there's also Wallops Flight Facility. It's NASA's only launch range that NASA owns, and they launch frequently. They're launching an Antares rocket to the space station next week, November 2nd, and they launch these sounding rockets there quite commonly, a few times a year. So it's a lot easier to get to than Florida, and it's a lot simpler to get a close view if you want to watch some launches from there and go and have some oysters or something while you're down there. So what is atmospheric escape? As was mentioned earlier, and if you went to the 2014 talk at the library here, you heard about the MAVEN mission. MAVEN is a mission to Mars that is trying to understand where did Mars' atmosphere go. And that the answer to that is multifold. Mars is a lot smaller than Earth, so its gravity is weaker. And so if the atmosphere heats up a little bit, the gas can just kind of boil off into space. That's one answer. But the answer that we're really interested in is how does the radiation from the sun, both direct electromagnetic radiation, photons, light, how does that sort of enhance that escape rate? And then also the solar wind, which you're going to hear about in a second. That's basically a stream of particles that blows out from the sun, just like a wind here on Earth, except it's many thousands of degrees, and it's moving at 400 kilometers per second. But it's the same idea, and when that impacts the upper atmosphere of the planets, it can basically strip off that atmosphere. And over time, over millions or billions of years, it can totally erode a planet's atmosphere. So Earth does not have that problem because we're more massive. We have more gravity to hold on to our atmosphere. We also have a magnetic field that protects us to some extent and shields us. But by studying Earth and Mars and other planets together, we can kind of get a picture of how these different processes might work. So that's what we're doing here. Just so you can be reacquainted with the Earth's atmosphere, if you saw Sarah Jones's talk last year about the Icon and Gold missions, she may have covered this. For those of you who weren't here, we're living in the troposphere down here, this yellow block, which is sort of where all the weather on Earth happens, all of the thunderstorms and the rain and everything else, the wind we're having today. As you go up to the stratosphere, that's where your planes are flying when you go across country. And that's where the ozone layer is, the jet stream, and various phenomena like that. Those two are probably very familiar to you. But as you go up in the upper atmosphere, these are the spheres that Stephanie was mentioning. We have the mesosphere. Meso means middle. It's sort of the middle atmosphere. It's kind of a transition region. It's where meteors burn up as they enter our atmosphere. It's where you have a lot of perturbations that are generated by thunderstorms and tidal motions on the surface propagate up through that middle atmosphere, and it's a lot of dynamics that happen there. As you go higher up, you go to what we call the thermosphere, and it's called that because it's very hot. And the mesosphere is the coldest place on Earth. It's very cold there, and then as you go up in altitude, the combination of ultraviolet light from the sun and various processes tend to heat that atmosphere above the mesosphere, and that gets up to 1,000 degrees or even 1,500 degrees. So that's where the space station orbits, sort of where our low Earth satellite orbits are, and that's where we're studying our phenomena, sort of that thermospheric region. Co-located with that in kind of a weird way is the ionosphere. The ionosphere is the portion of the atmosphere there that is ionized. So it's only partially ionized. It's maybe 1% or 0.1%. But that 0.1% that gets their electrons and the ions separated makes a big difference in how that whole atmosphere functions. What you basically have is this phenomena where you have, instead of just one gas, like you go outside today, you're going to get a windy day outside. Now imagine going outside and having a wind blowing from this direction that's kind of cold and a hot wind coming from a different direction. That's the kind of things that happen up at these altitudes. You have a thermosphere, and that's the neutral portion, and co-located with it is the ionosphere. And that region is really interesting. There's a lot of things that happen, and we'll talk about some of those phenomena today. The ICON mission, which launched last week, is studying that region, and I encourage you to go check out their results as they come available. They're going to have their first light in December. So why do we study this region? Sort of the fundamental nature of our planet. We want to understand how the planet works. We want to understand how these gas-plasma interactions, the ionized gas, the neutral gas, how do they work together? Because they're very complex, and it's sort of this whole region is sort of a coupling region where you have energy coming from below, you have solar energy coming from above, and then you have energy from the near-Earth space environment, this auroral energy and related topics that kind of also put energy in from above. And they meet in this middle region where we're studying. And what we're going to show is that that meeting is what gives you this ion escape, atmospheric escape that we're going to talk about. We also do it, as I said, for comparative planetology. You want to understand other planets, start with the Earth. And then we have space weather. If you want to understand how radiation belts are changing around the Earth, or GPS communications are modified, those GPS communications travel through the ionosphere. And if it gets disturbed or structured in certain ways, it can interfere with those radio signals and cause problems with technology. So this is sort of just the big picture of where we are, and we're going to be focusing on that upper area, say from 250 miles to 500 miles is about where we're focusing with these rockets. And so we're actually going to be flying above the altitude of the International Space Station, but it's moving so fast that it's orbiting, and we're just going up and then coming back down. So this is the solar wind that I mentioned. This is a picture from the MAVEN mission showing the Mars sort of just embedded in this stream of gas, and this just streaming out from the sun, and it's kind of always there. Sometimes it's slow, sometimes it's fast. But the key point is it's carrying a lot of energy. It's carrying so much energy that it can just either directly impact the atmosphere and pull gas and neutral particles off, or it can actually set up currents in the atmosphere, and those can act like almost like heating elements in your toaster and boil the atmosphere off. There's different schemes by which that interaction can cause atmospheric escape, and we're going to study several of them with our rocket mission. But this is the primary source of atmospheric escape. This and the ultraviolet radiation that doesn't make it to the ground mostly, but it gets absorbed in those upper atmospheric layers and heats it and causes it to boil or escape. I mentioned this other sources of energy. There's the aurora. This is a visible signature. When you go to the high latitude regions, have anyone seen the aurora? If you raise your hands? Okay. We should immediately, after this, we should make a trip to Calgary or Alaska or Montreal, and we should go because it's fascinating and it's beautiful and it's you can't even describe it. I mean, it's just one of the things where if you saw the eclipse of the sun a few years ago, the big eclipse, it's like that. It's your brain can't process it at first. It's just kind of this, you're used to seeing certain phenomena in the sky. The sun is there, the stars are there, and here's something that's just out of your day-to-day experience. And we study this because it's interesting physically, but it's also sort of a diagnostic of how energy is dumping into our atmosphere. And typically what we find is where the aurora is very intense, that's where the atmosphere is escaping more. And that's not an accident. Those aurora are generated by electrons that are heated up in space and shot down into the atmosphere like rifle bullets, and those rifle bullets then tend to kick things out of the atmosphere. So this is just an artist's conception of what that atmospheric escape might look like. You kind of have this wispy, it's hundreds of tons of material, but that's over the entire globe over the whole day. So at any given moment, you wouldn't even feel it if you were to hold your hand out there. I don't recommend it. But it's just very light, but over time, it's sustained, it becomes a large outflow of atmosphere. So why do atmospheres escape? When we look at these comparative planetology that I mentioned, you can look at each planet, and primarily its gravity determines the escape velocity. The size of the planet determines the escape velocity on the vertical axis, and the temperature of the planet is determined by various things, including how far it is from the sun. And so if you combine those two things, if you have a big planet like Jupiter or Saturn, it's very massive, and it holds on tight to its gases. And if it also happens to be cold, then those gases don't have a lot of energy to overcome that gravity, and it can trap basically every gas we have. Hydrogen, helium, and so on are all trapped on planets like Jupiter. That's not quite true. This is only true for the thermal escape process. Even at Jupiter, NASA's Juno mission is finding escape processes like these because of the electromagnetic interactions. But if you just look at basically heating it up until the atmosphere boils off, that would not happen at Jupiter. For Earth and Venus, we're kind of an intermediate range where hydrogen and helium are light enough that they can just boil off into space. And we lose hydrogen and helium at a constant rate, basically. But if you get to oxygen and heavier gases, they are gravitationally bound at Earth. So they stay here. Except not. We see them in space, and we know it's coming from the Earth. So just the thermal picture here is not good enough to kind of explain what's happening. As you go down to smaller planets like Mars, even though it's maybe a little colder than Earth, it's small enough that it can't even hold on to oxygen. So when you look at what's happened to its atmosphere, it can just free escape, even if there wasn't the solar wind and ultraviolet radiation also intensifying that atmospheric loss. So we lose hundreds of tons of atmosphere per day, much more than is accounted for by this simple thermal escape process. We happen to gain 200 tons of meteoritic material a day. So it's on net about a give or take. Our atmosphere will be around for billions of years, so there's nothing to worry about. But that's not necessarily true for other planets. So when we talk about comparative planetology, here's the MAVEN story on the left is Mars. There's no magnetic field. It's a small planet. The solar wind impinges directly on the atmosphere at all latitudes and just basically kicks those ions and neutral gas away. The Earth has the benefit, or maybe detriment, we'll see, we're starting to study this question, of having a magnetic field. The magnetic field kind of holds this charged solar wind away. It's an electrically charged gas, and it can kind of repel that gas. from the low latitude regions around the equator. That's where those field lines, those magnetic field lines, those blue lines, are sort of acting like a shield or a bubble. You can see at high latitudes near the poles, those magnetic fields are more vertical and more like a funnel. And the kind of one of the current dichotomies we're trying to understand is to what extent we know at low latitudes the magnetic field is a shield. At high latitudes, though, it almost acts like a sail, where it actually expands the region over which we can get solar wind energy and concentrates it and focuses it into these narrow regions at the poles. So even though the overall loss rate might be less because of the magnetic field, in those high latitude regions it's probably much, much higher than it would be without the magnetic field. So there's kind of a give or take there, and we're trying to understand that. And the reason we go to Norway and we go to these polar regions and why the aurora happen at polar regions is for this very reason. It's because the magnetic field is essentially an open funnel that can let energy in at high latitudes. So there's a very big difference there. So this is some work by my colleague Catherine Garcia-Sage at Goddard. She is studying what might happen on exoplanets. And there's been a lot of exoplanet discoveries, thousands discovered in the last few decades. And there's even a Nobel Prize awarded recently for the first exoplanet discovery. And now that we are discovering them, we'd like to try to predict what are they like. You know, and we're not quite to the point where we can fully characterize their atmospheres or their planets, but we want to try to understand it as best we can. So the first thing we do is we try to make some predictions based on what we know about Earth and Mars and Venus. And this is a case that she ran for Proxima Centauri b. This is way down here in the bottom left. That's the nearest exoplanet to Earth. And you're familiar with this term, the Goldilocks zone. The Goldilocks zone is one measure of habitability of a planet. If life was to be like Earth life, then it would require liquid water. And to require liquid water, you need a certain surface temperature that's not freezing and not boiling. And depending on the size of the parent star, you can be a certain distance away from that star and still have a temperature that gives you liquid water. So that blue region is the Goldilocks zone with some boundaries, red and orange, depending on how loose that is. So if you just did that, purely what's the temperature of the surface of Proxima Centauri b based on its star and the distance from the star, you'd say, oh, it's at the right temperature to have liquid water on the surface, and might there support life. It turns out she did a study that using what we know about the solar radiation, the ultraviolet radiation from that star and its likely stellar wind, under certain circumstances, that an Earth-like planet put at the location of Proxima Centauri b would have lost its atmosphere in a very short time, in 1 billion years or so, much shorter than the Earth's lifetime. So this kind of work, trying to take what we know from Earth and Mars and try to predict what we'll see with James Webb Space Telescope and other future missions that are going to study the atmospheres of these planets, is helpful for us to target, you know, planets that might be of particular interest. And Proxima Centauri b, being the closest, you'd think would be a great target. This is a very interesting prediction that Katie has made to try to understand whether that is likely. So this is just, in summary, what we're trying to do. These auroral electrons come in, they shot in from space, they create the aurora, and through various mechanisms, which I'll talk about, they heat hydrogen, helium, oxygen ions, and those ions then escape. And the oxygen are the ones I'm focusing on because they're the ones that are hardest to get out. The hydrogen and helium, as I said before, basically just boil out on their own. They do get enhanced during these periods, but it's not as big an effect. The oxygen goes from nothing coming out to a huge fountain that dominates the escape during times when there's strong aurora. And the mystery about it is the escape velocity for this gas is 11 kilometers per second to overcome Earth's gravity. They start at about 1,000 Kelvin, which is about 1 kilometer per second. And by the time they escape, they've accelerated 10 times in velocity or 100 times in energy just to get out of the gravity well. And we've even seen Earth source oxygen ions that have energies of 10,000 electron volts or 100,000 times more than they started with. And the mystery is, how does that work? And it has to do with the fact that you have electric and magnetic fields and you have ionized gas, and those electric fields can basically push on the ionized gas and accelerate it. So if you have a neutral gas, you can't really get that phenomenon. It's hard to push on neutrals other than by colliding with other neutrals. You can't really get large amounts of energy into them. But an ion, you put electric field on and you just accelerate it like a linear accelerator, it will just take off and gain a lot of energy. So it's not as simple as that. We don't have just single battery that can kind of accelerate those ions, but we do have different processes that can give energy to them over time. And one of the ones I'll talk about is waves. So in other words, variations in the electric field that can kind of push on ions, and like pushing on a child on a swing, if you push on them the right way, you can build up a resonance and build up a lot of energy in those ions. So we'll talk about that at the end, but this is basically the picture. Electrons in, ions out, and we're studying what makes that connection between this energy source and these ions leaving. So we talked about Parker Solar Probe maybe before this started, and just want to talk about a little bit more about that. Parker Solar Probe is doing some great stuff. They're on their, I think, third pass to the sun. And one of their major goals is to understand how the solar wind, which is accelerated from essentially zero velocity to hundreds of kilometers per second. And the way they do that is by traveling close to the sun. You can see this plot here. As you start out close to the sun on the left, the solar wind has no velocity, and as you go out to the right, it's sort of tapering to a steady state. And they're going to this region where the acceleration, the velocity of the solar wind is changing and accelerating. So they go in there and they study what makes that accelerate. The auroral wind, or the polar wind, or the atmospheric escape that we've been studying is very analogous. There's different processes driving it. We're not as hot as the surface of the sun. We don't have as much magnetic energy in the same way. But we have different kinds of mechanisms that also give you this sort of 0 to 10 kilometer per second energization in a very short, narrow window. And that is a window that fortunately you can reach with sounding rockets and also satellites. And we have these two rockets up here just sort of schematically showing you we're flying over the aurora and we're trying to get into this altitude region where the acceleration happens. So we talked about sounding rockets. I want to just, for those of you who aren't familiar, these are very inexpensive but very powerful scientific tools that we use. They've been flying since the 1950s, and they, for us, our home of NASA sounding rockets is at Wallops Flight Facility on the Eastern Shore. And they have a stable of different vehicles. They're kind of always updating these. The main things about these vehicles is they have some combination of standard features and some combination of custom features, and that keeps the cost down. You know, things that we don't want to reinvent every time, like the batteries and the telemetry. They have a very experienced team and very good designs, and they just keep building those, and maybe they improve them over time, but they're not reinventing the wheel every time. And we put our energy into inventing new scientific instruments to fly on these standard missions. And you can see they've got a whole host of rockets from one-stage vehicles. They've even got some four-stage vehicles there. And depending on what you need to do, how high you need to go, and how much of a payload you need, you choose a different variety. And they're something like 20 to 60 feet long, these rockets, and they're, you know, with fully loaded, maybe up to 3,000 pounds, 4,000 pounds. So you got to get an idea. They're about a foot and a half in diameter, and we can launch 2 or 3 of them pretty straightforwardly in a period of a week or 2 weeks. And the Grand Challenge is a case where we're trying to do even more. We have an international collaboration with Norway, Canada, and Japan, and the UK. And we have taken 9 missions with a total of, I think, 13 rockets to 2 sites in Norway. And over a period of 2 years, we're launching those and using the ground-based assets that are radars and telemetry and cameras and things to kind of leverage all those together. So we don't have to pay for 6 individual or 9 individual campaigns and ship everything 9 different times. We can ship everything once or twice, do our missions all at once, and then also exchange data. Just like the library you have serve as a repository of knowledge here, the Grand Challenge, we're trying to build up these databases and make them publicly available and accessible and archivable and all that sort of thing, so that we can use those data 50 years from now or 100 years from now, because I think this is kind of a unique time. So this is the Grand Challenge Initiative. This was the brainchild of Professor Göran Moen at University of Oslo in Norway, and Kolbjørn Blix there also. And what they did was they kept working with the Norwegian government and U.S. government and Japanese government to try to get these missions together and then try to synergize them and synthesize them a little bit. And so we have 9 missions. I guess it's 12 rockets. Always get that wrong. And you can see just different schemes of what they're doing. We're studying ion outflow atmospheric escape. There's a couple other rockets doing the similar thing. But there's other rockets doing different phenomena that have to do with heating of the atmosphere in different ways. But basically the same. There's even a student rocket where they got university partners from all over the US and Norway and Japan and had them build 6 different experiments and launch their experiments into space, which was a great opportunity. So this is the Grand Challenge. It's the first Grand Challenge. We're hoping to do more with different topics, but this is the one that we started with. And why do we go to the cusp? We say it's the Grand Challenge in the cusp. The cusp is this region where the magnetic field is basically open to the atmosphere. It's basically a funnel or a weak spot in a protective bubble. And if you want to study Mars, Mars has no global magnetic field. So the solar wind comes in and touches the atmosphere. Well, this is the one place on Earth, there's 2 of them, one in the north and one in the south, where the solar wind touches the atmosphere. And so if you want to kind of replicate that phenomena. We've also done studies of atmospheric escape inside that bubble, which has different phenomena. But this is sort of the piece where we make that link to the Martian environment. So these cusps are very important. So this is the grand challenge again, just in more detail, and you can see these different trajectories. We go to different altitudes. We're studying different phenomena, some in the mesosphere, some in the thermosphere, and some in the top side of the thermosphere. And some of them we launch one rocket by itself just to study something. In the case of Visions 2, we launched one rocket and then 2 minutes later another one in the same trajectory. And depending on which mission we're talking about, they have different schemes like that to try to get those multiple point measurements. Is sort of a new thing for us, is to try to, instead of having a single measurement for 5 minutes, we do multi-point, either spread out in space to get spatial gradients measurements, or spread out in time to get temporal gradients and variations. So this is all kind of a sort of new territory for us. The sounding rockets, as I mentioned, they go up into these different regions of the atmosphere, and the way it works is you launch, and after a while your engine will burn out, and you just coast ballistically. Just like you throw a ball in the air, the rocket is just going to come up and follow a parabolic path and come back down. That's in contrast to these satellites, which are essentially coming across in a horizontal fashion, and the balloons, which are at lower altitude and just kind of stationary and floating around. And they can make very long duration measurements. They can hover, basically, and make long duration. The satellites give you a synoptic global view, and the rockets give you that high resolution and altitude profile view, which you can't get any other way. So they typically last 5 to 15 minutes. We go between 40 and 600 miles, and we can carry 100 to 1,000 pounds. And we can do that all for a couple $1 million, which sounds like a lot, but compared to hundreds of millions or billions of dollars, it's very cheap. So here's just an animation of that video. I'm not sure why that is playing. Okay. Oh, there it is. That's the reason. I wanted to show you what the sounding rocket looks like when you launch it. You may have to sit through that initial one again. Okay, let's just watch this. This is just an animation of those rockets launching over time. And you can see some of them have multiple payloads and multiple things they can deploy to make the measurement. Here's what it looks like. This is from a Wallops flight facility. This is launching out over the ocean. This is from Alaska. We have different launch sites all over the world, and these two in Norway are 2 of our prime sites. Here's the grand challenge we've done. There have been these missions, and 5 of them have launched already, and all fully successful. That includes last December and January, and then in April this year, including the student rocket, which launched in January, and those students were very excited to get their results back. We're starting again. We kind of go in the winter because we want to be there in darkness so that we can get aurora and we can get our cameras viewing those. And so that's when we go. And so they're starting again November 26th, the next window, and they're going to launch the Chi mission, which has Japanese involvement, and the C-Rex 2 mission, and also the IC-5 mission, which is the Norwegian-led mission. The Japanese mission, another Japanese mission is down the road, perhaps next year, perhaps the following year. So these are what the rockets look like when they're launching. Visions 2 is my favorite. It's time-lapse exposure where we just caught both rockets in the same exposure. Trice 2 had 2 rockets. The G-Chaser is the student rocket. Caper 2 is another scientific single rocket. And Azure is another rocket that made some measurements in that region. Here's what they look like just for your benefit. Again, one of the reasons these are so inexpensive is because they're not guided. They're basically, these sounding rockets are basically a tube of aluminum with not gunpowder, but essentially gunpowder inside. And they just light it, and whichever direction it's pointing in when you light it is the direction it goes in. So we do it like a bottle rocket, if you're familiar with these. Basically hang these rockets off of a launcher that has a little grippy lug, and you point the launcher the direction you want it to go, and then you trigger it, and it goes. And in this case, we had 2 launchers. The Norwegian government had to build a second one with NASA involvement so that we could launch 2 within 2 minutes of each other. And this is just sort of what it looks like. We've got, in this case, a 3-stage rocket. A Terrier is the first stage, Black Brant, Nika. The Nika is interesting. It doesn't have any fins. It's burning exoatmospherically above the breathable atmosphere. And so it doesn't have fins because there's no air pressure to stabilize it. We're already spinning at that point for stability, and it just lights, and it just goes. And we separate those stages in the usual way, and then at the very end, our payload is separated. We have 2 payloads, as I mentioned. These are both sort of what's hiding under the nose cone is this. You know, this is 12 feet long and about 1.5 feet in diameter here on the left, and 16.5 feet long. And the one on the left is basically our Steadicam. You know, we're watching the aurora. Usually you see the aurora from below, but you've seen maybe some videos of the ISS where they're viewing from the side. This one is viewing from the side, and that gives us very important information about the height distribution of the aurora and what kind of energy is putting in, what kind of gases there are there. So he launches first at 11:06. We launched on December 7th. It goes to a little higher altitude, 800 kilometers, to get some more hang time, to hang out longer. This guy launches 2 minutes later, and it's the one that's actually measuring that escaping atmosphere due to the auroral input. So together they're kind of a team, And it was a lot of work for the Wallops team to get those two synchronized and get them working, but they did a great job, and both launched with very high success. So now that you know what the rockets are and what we're doing, I'll tell you about where we're going with this mission. So it's an archipelago called Svalbard, which the largest island is Spitsbergen. And then within Spitsbergen, there are two towns of note. There's Longyearbyen, which is sort of the administrative center, and that's where most people go. You can go there as a tourist anytime. Very interesting. There's the famous seed vault, Doomsday Seed Vault, if you've heard about that. That's in Longyearbyen or nearby. You can go look at the aurora there and go look at wildlife. And then Ny-Ålesund is a research town. It is owned and operated by a private company, sort of a public-private partnership in Norway. You have to have business there to stay. Some tour operators will offer you a day trip. Usually if you stay in Longyearbyen, you can go to Ny-Ålesund for the day. Anyway, this is at about 79 degrees north, and Ny-Ålesund is the northernmost inhabited town. And it's really amazing place for us to go because it's basically perfect for this facility, and I'll tell you that in a second. So if this is the map looking down on the North Pole, Spitsbergen, Ny-Ålesund is the northernmost permanently inhabited civilian settlement. So that's a little bit of a caveat, but there are some military bases, of course, further north than that, and some other places that close in the winter, but there are people here all year round. In fact, we went in the winter on purpose. And in that winter, the town is 35 people, and we brought 60 people, so you can kind of imagine but they're used to bigger groups. They just had to accommodate a little bit. The reason we go there is there's an ice-free harbor. The harbor master has his place there, and every couple of months a supply ship comes, and we shipped our payloads there by ship. There's an airport which has 2 flights a week, and then the beauty of it is that cusp is a high latitude phenomenon. It's kind of localized, and as the Earth rotates, it stays fixed. It's always pointing. The cusp is always pointing sort of towards the sun. Every day, this rotates under or near the cusp, and it's the only inhabited place with a harbor, an airport, kitchen and bathrooms, and a launch pad that goes near the cusp. So it's really unique. We started launching rockets from Ny-Ålesund in 1997. There's another launch range further south on the northern coast of Norway in the Lofoten archipelago that's been used for a long time, but this is a sort of a new launch range. The Norwegians started in 1997, and NASA followed right after. And then we've launched about a half dozen rockets from Ny-Ålesund in the last 20 years. So it's about 769 miles from the North Pole. We're not the first to use this as a unique location. The first verified journey to reach the North Pole was taken from Ny-Ålesund. The Roald Amundsen and Umberto Nobile from Italy, Roald is from Sweden, they took the airship Norge and they flew it to the North Pole. And even though previous attempts had said they'd made it to the North Pole, they're the first ones that could actually verify it with their navigation charts. And so that was in 1926. It didn't have a happy ending. After this, Umberto tried to go again, and he had a crash, and Roald Amundsen crashed his plane looking for them, trying to rescue them, and neither one survived. But it's that first case was very interesting, and you can still see there's just really a lot of history there in this area. They had a lot of coal mining and a lot of other aspects that make it very unique area to visit. This is the town itself. This is it's about maybe a quarter mile, half a mile long, and you walk everywhere. There are vehicles there, mostly just for carrying equipment and things like that. But if you're a person, if you just have personal business, you're walking everywhere. The reason you have to stay inside the town boundary is because of the polar bears. Essentially, this is your life for 6 weeks. If you go outside, you've got to go with someone who has a gun and knows how to use it, because you don't want to shoot the polar bears, but you want to be able to defend yourself, or maybe shoot into the air to scare them, that sort of thing. But you just, you don't wander outside. People do have dogs that can alert them for the polar bears. In the winter, they're not as much of a problem because they're out on the ice fishing. So that helps a little bit. On the other hand, it's dark, and if you did run into one, you wouldn't have time to do anything. So we keep ourselves within that sort of confines. It's actually a pretty lively town. They have a store that's open a couple days a week for a couple hours, and people congregate there, and there's a bar, and there's the usual. And people are amazingly friendly. It's dark 24/7. You're there. It's just sun is just setting, I think, this week. Started the long polar night that goes until February. And but it's amazing. We were there over the Thanksgiving and sort of just before Christmas, and they treated us very well. And I'll talk about that in a second. But just a very warm community. I thought I have a sort of seasonal depression. I thought I would be depressed for 5 weeks. It was amazing. I mean, you had never had a moment where you were kind of sitting around. You had always something to do, always some social event or some. They even have lectures. They have people coming and talking about history and this sort of thing. So it's a very intellectually vibrant community too, as most of Norway is, I think. So this is sort of what the challenges of going there are. It's remote and isolated. Even though they have this harbor and this airport, still, if you forget something, there's not a Walmart or something down the street. So you've got to plan ahead. There's a lot of ice. You know, we have people, early on, were slipping a lot because it had rained there, which is very unusual. And then the ice just stays and just freezes. And so you have to watch out for that. The darkness is 24/7. The moon is bright sometimes, but when it's not there, it's very, very dark. The polar bears, we didn't actually see any, but they are there. It's also an environmentally sensitive area. They have a lot of sampling of, there's a lot of research that goes on there for pollution research, snow and glaciology research, and their marine biology, and they don't want you to contaminate their research samples, essentially, with your rocket plumes or your Teflon or whatever. You know, we have this styrofoam cage, for example, that goes around the rocket to keep it warm when that's just sitting on this launcher. And when the rocket launches, it just bursts through that styrofoam and breaks the styrofoam into a million little pieces that go onto the tundra. So what did we have to do? We had to go out right after the rocket launch and go out with trash bags and pick up every one of those pieces. And someone said, well, why don't we wait till tomorrow morning when it's light out? And I said, well, you're going to be there for 2 months. So it was one of those moments, and I kept thinking it was like a science fiction movie or something, or the horror movie. You know, we're all out there kind of bent over like this, and the polar bears are just kind of like, you know, just on the edge of the light waiting for us. Fortunately, they kept away. It's very windy there. It's, you know, because the way the Gulf Stream works and everything, it's commonly very windy. When we launch the rocket, again, it's not guided, so you can't have a lot of wind when you launch it, or else it'll go out in the wrong direction. There's also a radio quiet zone. This was one of the biggest things to adapt to. They have this really sensitive tectonic measuring the tectonic plate shifts, and the way they do it is by some kind of radio astronomy technique, which I'm not familiar with. Just these very giant 34-meter, you know, radio dishes that are constantly on, very sensitive, and they have to point different directions. If they point back towards the town and you've got your cell phone or your Wi-Fi on, it will contaminate their measurement, and they'll have to start again. You know, and these are the things that take decades to run these experiments. So they're very serious about no wireless of any kind. It was actually kind of nice because it forces you to interact with each other, you know, which is surprising these days. But it was really a lot of coordination, because we have to, of course, we have radio transmitters on our rockets, so we had to coordinate with them. Hey, we want to test. Can you look away for a while and then look back, and that sort of thing. And our safety crews, which were Wallops and NASA and the Norwegian crews, were very helpful at getting everything going. So these are just some pictures my friend Chris Perner, who works with us, had taken. If you're a photographer, this is a great place to be, even though it's dark. Just get a long exposure, and there's a sort of this is called the Zeppelin Fjell, which is the Zeppelin Mountain in the background, and there's some aurora and stars. And this is a graveyard of some coal miners that are there. They have a lot of monuments to the coal miners because it was a very hazardous operation, and a lot of people lost their lives. And then in the bottom right is just some more aurora. I think that one's a little bit retouched, but he did a great job. But you get an idea of this aurora. The thing about it is it's very structured. You can see all these little beams. It's not sort of a smooth curtain. It's got all these little tiny filaments of light in it. And that's going to be very important for what we talk about later, how this atmosphere gets heated. So how are we doing? Okay. So this is just the life there. You know, they were very good to us. They actually made us an American Thanksgiving. It's not their holiday, but we shipped over some turkeys and some mashed potatoes and things, and the kitchen really was nice to us, really gave us a great American holiday. They have social events almost every day. My favorite was Stick og Drik, which means knit and drink, and you go there and you enjoy some of each. Trivia nights, hockey, you know, different things. Just beautiful social events there. We even had the world's northernmost karaoke party. That was I'm a karaoke DJ, so I enjoyed doing that. And they got their own special beer there. So just great living there. So let's talk about the launch conditions now that we've seen sort of what it's like and why we're there. We launched on December 7. It was the 5th day of the window. These windows last about 2 weeks. Typically, we do it when the moon is down so that we can have our sensitive cameras look up without having moonlight contaminating us. So we have about 2 weeks. And just for budgetary reasons, you can't stay there for a year. So you get 2 weeks to get your chance, and if something comes, you launch. And if it doesn't, you might launch into something not as good, or you might go home. So it's a little bit hair-raising. You'll see that at the end of the talk. What we do to figure out if we're going to launch, the issue is that's not really shown well here, but I'll show you in the movie. The cusp that I talked about, I showed it as a static thing, but it's really moving around a lot. It kind of wiggles back and forth, it wiggles side to side, and that depends on how that solar wind is blowing. If the solar wind is blowing very strongly in a certain direction, as the magnetic field in a certain direction, the cusp will tend to move south. Otherwise, it moves north. It can move east and west. And then the Earth is rotating under it. So in the Allison, you've got your fixed rocket trajectory, which is, for safety reasons, has to be in exactly one direction. You can't swing it around. And the cusp is doing this, and you're trying to figure out when's it going to be where I want it for 10 minutes during my rocket flight. After 10 minutes, it can go away, but it moves around on 10-minute time scales. So you really have a lot of, waiting by the trigger, basically, to make it happen. And so we had this really expert team from the Norwegian group, Andres Spicher and Hjalmar Aksevik and Jørn Moen, who'd been there many times and sort of knew what to look for. And the main thing we used was these upstream solar wind monitors. There's one called ACE, there's also Discover and Wind, and they basically sit about 45 minutes upstream of the Earth, and they're basically like weather buoys. And they measure, hey, what's the solar wind blowing now? And they radio back, and you've got about 45 minutes to say, okay, in 45 minutes this magnetic field is going to be south, and the cusp is going to move, or the solar wind velocity will pick up and we'll get more intense aurora, whatever you want to do. The problem is it's not always 45 minutes. Sometimes it's 45, sometimes it's 50, sometimes it's 60, and it sort of depends on the detailed geometry of where that satellite is. Sometimes it's a little bit off the center line. Sometimes the solar wind velocity is a little faster, and you have to be constantly flexible and adjusting. And what you're looking at in this top red curve, that dashed line is 0, and that's the north-south component of the magnetic field in the solar wind. And all you have to know is that when it goes south and turns negative, we get more aurora, and the cusp moves south, and you get more atmospheric escape. And when it's north, you get less. So we want to launch into a southward aurora, and we only have about 4 hours or 5 hours every day where we can launch, and we're just watching the solar wind do its thing. And then when it happens, when it goes south and stays south for, in this case, about half an hour, 25 minutes, we say, okay, we're going to launch 45 minutes from now. And you're just kind of watching that all the time, and you're watching your local radars and your local cameras to see what's happening. And if this movie on the right works, it will show you sort of what it looks like. This is ground cameras looking up at the aurora in red light and green light, the top two panels. And the dot is where the rocket is launching. So we actually hit it pretty well. You can see, it's kind of hard to see if we watch it once, but you can see the rocket is passing right through that auroral region and getting the measurements we need. I'll see if I can back it up and do it again. And it's just showing one of the two rockets. The big flash is when the rocket launches. That's what drowns out the camera. So we use these cameras on the ground to tell, is the aurora in the location where the rocket's going to be? And we of course, sometimes the rocket hooks or slices and we miss this. In our last rocket, Aurora, in Alaska, we had two aurora. We went right between them. It's kind of a dicey business, but it usually works. So our initial results. I want to make sure we're on time. We observed some atmospheric escape with visions. We measured those energy inputs, those electrons and those waves that drive the escape. And we got some brand new information about the electric waves that may be responsible for heating these ions. As a bonus, we think we're seeing evidence that even heavier species beyond oxygen, molecular nitrogen is being uplifted. So that's twice as heavy as atomic oxygen, and it comes from even lower in the atmosphere. So it's a big mystery how that gets there, because what should happen is that molecular nitrogen should be collisionally damped. If you put energy in, you might heat up a little bit of nitrogen, but then it runs into another nitrogen and gives us energy up. So how does a single nitrogen get enough energy to escape? That's a hard process to understand, but we think we're seeing that here. So I'll go through these one by one. Oh, so just to give some context, this is what I mentioned. We have this Steadicam, which is the rocket-borne camera, just looking at the aurora from the side. And I think we'll start with the last one, which is the nitrogen molecules. I don't know why does it, there we go. Nitrogen molecules uplifted. What you're looking at is the rocket-borne camera. So it's actually looking back to the north, back towards Ny-Ålesund. The sun is behind us. We had to have that so that we couldn't drown out the camera with the sunlight. And the rocket is going up and then coming back down. And as it does that, it flies over some aurora and then basically getting a side view of some aurora at the very end. And there are 4 different colors. We basically have very narrow filters to look at a red line, which shows a particular kind of electron emission, high energy electrons on the green. This is some information about the oxygen gas, and this is the nitrogen gas in the bottom right. And so what you're seeing, the curve of the Earth there, that's the limb. You're basically looking over the horizon. This bottom sort of semicircle, that's the auroral arc that we're passing through. So that's just a region where the aurora is bright. And then as we go through, at the very end, you're looking at the atmosphere, you're looking up, and the vertical direction tells you what altitude the emissions are coming from. So from the ground, you can't tell that unless you triangulate or something. For a single camera, you can only see, hey, there's light there, but I don't know where it's coming from. With this technique, we can say there's so much at 100 kilometers, so much at 150 kilometers. And what we're finding in the bottom right, if I can just skip ahead, this is the bottom right shows that nitrogen gas, which shouldn't be there and is actually quite intense, and it's actually at higher altitudes than the red and the green emissions. So normally that would be down lower, and that would be a signature of that nitrogen gas that's escaping, and we're seeing it here. So that's very interesting. That was one of our first results. The other kind of sensors we have besides the camera is that second rocket, and that's what's actually measuring the details of the atmospheric escape. It's measuring very high resolution, what are the electrons doing, what are the electric fields doing, and what are the ions that are escaping doing. And this is a complicated picture, but basically there's electrons in the top, which are the energy source, and there's ions in the bottom three panels, which are the result. And so the most important is the top panel and the bottom panel. The top panel is electrons that are streaming down in the atmosphere, and what you're looking at is energy and time. And then the color is how many electrons there are in a given energy at a given time. And so the sweet spot is around 100 or 200 eV, right about where the bottom of that red band at the top is. That's where electrons can most efficiently give their energy to ions that can escape. If you go higher energy than that, the electrons tend to give up their energy deep down in the atmosphere, and then you have that problem of the sea of neutrals just sort of sucking the energy away. So we see that. And then when we down to the bottom, these are the ions that are actually traveling back up. So we're at 600 kilometers or so, and we're seeing these ions that are already heated to above escape velocity, some of them, that are streaming from below that 600 kilometers. That was a surprise to me. To previous measurements we've looked at, we see those ions already formed at 1,200 kilometers, 1,400 kilometers. So that already tells you something about what the mechanism is that energizes those. You know it's already active in that very narrow region between about 400, where that sea of neutrals disappears and you don't get that damping effect, and 600, where we're seeing the rocket. So that's clue number one, is we're already seeing escape, and we're seeing it at a low altitude. So that was kind of a nice result there. Just for completeness, this is some measurements. So that was provided by Jim Clemens at the University of New Hampshire. I want to say that this other measurement, the Steadicam, was provided by Jim Hecht at the Aerospace Corporation. This is provided by Rob Pfaff, my colleague at Goddard, and his team, and he basically has measurements of the electric waves at high frequency and sort of medium frequency. Then we repeat the electrons and ions here, and these are the electric fields in the bottom two panels, and then the density of the plasma. And the whole idea is to show you the context. There's a highly structured environment with lots of these little filaments you saw in that one image of the aurora. It's very localized. You get auroral here, but not here, not here, not. It's just very small filaments of that. And that's very important for the mechanisms that give you that escape. We get low energy electrons, which are efficient at heating these ions, and lots of electric wave activity in these top two panels that is also efficient at heating the ions. And the question is, which is more important? Are they working together? Do you get some heating from the electrons, and then the electric waves take over and give you the rest, or how does that work? So what we did was we took these two rockets, and if you recall, we had two rockets, one launched to a high altitude, another one launched a little bit lower 2 minutes later. But at some point, they're basically on the same vertical point. And you can say, what is happening here, and how do the ions look here, and the waves, and how do they look at a higher altitude? And this is the first time we've really done this measurement. Because with satellites, it's hard to coordinate that. You couldn't have two satellites very easily that could do that unless you do really fancy orbital design. With the rocket, it's very easy. You just launch one and then launch another one a little bit later and line them up so they're just at the right spot. So what we did was we measured these waves, and this is now frequency in the vertical scale, so it's sort of a spectrogram, and time on the right. And the color is the intensity of the wave. And so I want to draw your attention to two sort of bands of red. The top is the top rocket, the high altitude rocket. The bottom is the low altitude rocket. In each case, there's a band of high intensity waves at the higher frequencies, another band at the low frequencies. So we call the top band the VLF, very low frequency. That's sort of the upper end of your audio range, 10 kilohertz, 20 kilohertz, and a little bit below that. The ELF is the extremely low frequency down at the bottom. That's sort of 10 hertz, sort of low, low notes on the piano up to maybe A on the piano, 400 hertz or so, 600 hertz. So that's sort of the two different regimes, and there's sort of a gap in between. What we noticed is there's intense VLF waves at both altitudes, but the ELF waves are much stronger at the higher altitude than even this other altitude that's only 200 kilometers below. And so the mystery there has always been which is responsible, the VLF or the ELF. They have different characteristics, they're different efficiencies of energization, and now we have some evidence that we already know there are ions being accelerated below this rocket where there are intense VLF but no ELF. So you don't need the ELF, in other words, to get those. So that kind of gives us a nice, for the first time, I think, a little distinction between what's doing the job in this particular case. The problem we had before was we only launched high altitude rockets. So we would always see both waves, and we'd always see ions coming up. And you don't know where the ions are being energized. Are they happening where you are? Are they happening below? What are the waves looking like? So this is the first time where we've actually got a limit where we say, here's a region where we know there are ions and no waves of this kind, and there are waves of the other kind, and that sort of helps us in our understanding. So this is a kind of a first kind of measurement like that we've done. And what I want to do now, do we have another 10 minutes or so? Okay. So I've got a movie that was produced by our documentary team, Joy Ung and Miles Hatfield at Goddard. They came with us to Svalbard and did the measurements. I thought I would show that and then take questions. If on the other hand, if you have something that's burning right now, we could do that. It's about a 7-minute movie. It's pretty good. It'll be released publicly in about 2 weeks when they do the next start for the next Grand Challenge rocket. Any questions at this point, or should I just go on to the movie? Okay, I'm going to go on. Stephanie's advised me to go on, so I'll just, yeah, is it quick?
2 questions. Number one, assuming that you want to capture the rockets after they fall down, if they come down over water, how do you find them? And number two, if they come down over land, doesn't it scare away the polar bears? The rockets fall out of the sky all the time?
Can you repeat?
Yes, I'd be happy to repeat that. So the questions were twofold. One is, do we recover the rockets, and if so, how so, since they're landing in the water? And two, if they land in the land, is there any issue with safety or polar bears wildlife? In general, some of the rockets that NASA launches, we do recover. They have parachutes, and they have maybe an expensive telescope on board, and they want to recover it and fly it many times. And that's very common. But we typically only do that over land, and we only go to low altitudes, like 350 kilometers or so, about 180 miles. And the reason for that is if you go higher, you're coming in too fast, and the parachute can't really do the job to recover it. So we don't do that, partially because we want to go higher, and also because the payload has weight. The parachute has weight, and the recovery section has weight, and takes up part of the payload. We can't put instruments there. And also, if you remember the picture of our payload, it's got all these different things that are unfolding and opening up, and there's no real way to seal that against the water. So we have recovered them, but they're basically crumpled when they land on land. And in the ocean, we couldn't possibly do it. Walsh is developing some techniques to have like a vacuum sealed section where it would seal itself and then have buoyancy so you could recover it in the water. But that's still under development at this point. So then when we do land on land, what do? Well, the first most important thing is we make sure that there's nothing in our range that has human life or important infrastructure. When we launch in Alaska, we have to avoid the pipelines and things like that. And they're very careful, they're very conservative about how they make those analyses. We do care about the wildlife and so on. And when you go to Alaska, for example, they have an active program where they go out to the field and find these payloads and bring them back. And they have a bounty program where local people can go and get $1,000 for getting their snowmobile out there and saying, hey, there's a rocket here. They tag it, put the GPS location and so on. So we do care a lot about that, and we do try to clean up after ourselves, so to speak. Does that answer your question?
Yes.
Let me go on to the movie, and then we can take questions at the end. So this is a great documentary. I'm very proud of Joy and Miles for putting it together. And it's amazing what they could do with only about a week when they were in the field. Let's see if this is going to start by itself.
There's one thing that stands between us and the harsh environment of space, our atmosphere, the part of Earth that sustains all life. But here, in the closest town to the North Pole, it's slowly leaking away. A team headed there to launch rockets into the leak, but it's not the lack of atmosphere that they're concerned about. The leak is a natural process that will take billions of years, so we're not going to run out anytime soon. It's part of the larger story of how a planet's atmosphere changes over time, a key factor in the search for life on other planets.
We have 35 residents and 60 of our team together in a town that is completely isolated. There's a plane twice a week, and there's 1,000 polar bears nearby.
This is Doug Rowland, a NASA scientist who's taken his team to Ny-Ålesund on the island of Svalbard. The island lies beneath one of two regions near Earth's poles called the cusps. It's where we can access space directly, and where 100 tons of atmosphere escapes into space each day. This escape gives clues to how long an atmosphere will last, and ultimately, whether it stays around long enough to sustain life.
What we're trying to understand is how did Earth's atmosphere evolve over time? And how do other planets that might be like Earth or more dissimilar to Earth, how did their atmospheres evolve?
So Doug joined forces with Göran Moen, a professor at the University of Oslo, who started the Grand Challenge Initiative, CUSP. It's an international mission to launch 12 rockets into the Earth's northern cusp. And Doug, he's the mission leader for the first 2 rockets of the campaign.
We don't want to waste our rocket. It took us 3 years to make the rocket, only 15 minutes to use it, and I don't want to waste my shot here.
He's using a sounding rocket, which is different from the bigger rockets that carry satellites and humans into space. It's a small suborbital rocket that flies briefly into space, collects real-time data for around 15 minutes, then falls back to Earth. It's affordable, quick to build, and can launch towards a precise point.
The major advantage is that you can launch into a target on the sky.
But there's a limited launch window and only one chance to get the launch right.
We have these unguided rockets. They go where you point them, unless the wind is blowing, because the wind literally just blows them over. We don't launch when there's high wind.
So to measure the winds, they launch balloons with GPS trackers. They're released every 15 to 30 minutes, and then they're monitored to see how fast the winds are carrying them.
The ground winds were 12, 13 meters per second, gusting 17, which is way off.
You're filled with trepidation. Oh my gosh, this thing that I built, is it going to work after all this? So I think we're going to scrub for today. I'd like to thank everyone. I think it was a great performance. Thanks a lot.
This means that we are scrubbing this operation for today and we'll try again tomorrow.
The mission is named Visualizing Ion Outflow via Neutral Atom Sensing 2, or VISIONS 2. In short, they're looking at how oxygen is getting enough energy to escape.
It's a good test of how atmospheric escape works. Earth's gravity should hold onto the oxygen, and yet we see this gas shooting off into space. We're trying to figure out how that works.
That is a science question that has been hanging around for 4 decades.
Fortunately, anyone can see atmospheric escape at the right place and time.
In Svalbard we have the so-called polar night. It's dark all 24 hours.
This continual darkness is key for witnessing this. This is the cusp aurora. It's a type of northern lights that appears between 8 a.m. and noon, and you can only see it when it's dark during the day. It looks similar to the aurora that occurs at night, but when these iridescent colors dance at this hour each day, 100 tons of oxygen escapes from Earth's atmosphere into space.
This is our sport now to chase the aurora.
Working with them is the iSCAT radar and Kjell Henriksen Observatory. They have additional instruments to find the aurora.
Sometimes it's cloudy, so we use radars to track the cusp. And we can give advice that this is the right type of aurora.
This is the Wall of Science, a collection of data from satellites and ground instruments that helps them predict where the cusp aurora will be.
So the cusp actually isn't a fixed point in space, it kind of moves around.
What's controlling the cusp's movement is the sun interacting with Earth. Our planet is surrounded by a magnetic field that helps us hold on to our atmosphere. But at the north and south poles, the magnetic field bends inwards, creating a corridor between Earth and space.
When energy is released from the sun via a solar flare or coronal mass ejection, all of that energy in the form of radiation rides down the magnetic field lines of the Earth and is transferred and dumped into the Earth's atmosphere.
Electrons cascade into Earth's atmosphere. They accelerate and collide with oxygen particles, giving them energy to release light and sometimes enough energy to escape. Collectively, this forms the cusp aurora and streams of escaping oxygen.
This cusp is in constant motion.
And we've got a fixed trajectory. We really can't aim at where the cusp is. We have to wait for the cusp to come across our line of sight. Can you guys hear Kjellmar? We'd like you, as soon as you see an indication the cusp is moving close, to move it, the radar dish, if we can.
This is iSCAT. It's been very quiet, very difficult to launch.
Do you think we're gonna launch today?
No. Probably about a 60% chance of launching.
When we started seeing this really good data, this clock started counting down, and that's when everyone realized this is going to happen. We're going to launch.
We're doing everything we can to get that launch off before the aurora goes away. It is really, really challenging and nerve-wracking at that point. You can see the tension just rise in everybody when that happens.
And so everyone's watching their instruments, getting really excited, and then at T-minus 1 minute, all of us ran out to go see the launch happen. And then we immediately turned around and ran right back in to look at all the data that was coming back from the instruments. You know how much time and effort went into it because we all worked on it, and there's just nothing that compares to that feeling.
Everybody in every one of those little places, really just so happy to contribute to getting this science. It's really an incredible experience.
This is a story about what it takes to launch science instruments into space, but the real adventure will be in the data they sent back. Hidden within the numbers will be answers that reach far beyond Earth, shedding light on how atmospheres throughout the universe change, evolve, and perhaps support life.
Thank you for your attention. I guess if we have a little time for a little questions, how are we doing?
Thank you.
How often do you actually see an aurora? I mean, how often do they occur for you?
As they mentioned in the video, there's two different kinds. There's sort of the night side aurora where you see in Alaska, and the day side aurora which you see in this polar night. Both of them occur pretty commonly. The day side aurora is basically every day. Sometimes it's cloudy and you can't see it, but it's there. And the night side aurora in Fairbanks, which is one of the best places to go see it in Alaska, is every other night-ish, at the right time of year, the right season. And it depends on the solar cycle. Right now we're kind of going into a depressed part of the solar cycle, so it's less frequent, but still there. Yes?
How many experiments go up with each rocket?
That's a great question. The question was how many experiments go up with each rocket? And in our case, we had quite a lot. We probably had 7 prime experiments and then a bunch of experimental experiments, if that makes sense. We were doing a lot of technology development for the next generation of rockets, and we launched those where they don't have to work. We don't, and some of them don't work, but we try to keep pushing the envelope and try to test those. Some rockets have a single experiment. They might just do a single, really highly focused experiment. We try to measure different aspects of the space environment, so we need typically specialized sensors for each different case. Yeah. Yeah.
Where are the payloads fabricated? Where are they built?
Where are the payloads fabricated? When I think of the payload, there's sort of two aspects to it. One is the mechanical structure, that cylindrical sort of section and all the deck plates and everything, and also the electronics that sort of provide the infrastructure, the batteries, the radio, the attitude control system. That's all done at Wallops Flight Facility in Eastern Shore, Virginia. Then the instruments are basically bolted on. It's not quite like we're working with the engineers to design it hand to hand, but ultimately we come down with our instruments and attach them to that existing payload structure. And those are built at the home institution. So we have some at NASA Goddard in Greenbelt, University of New Hampshire, Aerospace, different, and we have Calgary, University of Calgary in Canada, and even the University of Oslo had some instruments on this rocket. Yes. Go ahead.
Yeah, I was curious about how the cusps seem to be, or the funnels seem to be pointed towards the sun.
That's right.
Even though the magnetic field looks elongated. I was wondering about that, and then also like the dynamic of the solar wind going around the Earth. Is it, are there any vortices in the solar wind?
Great question. Yeah. Great question. I mean, the question was, why are the cusps kind of pointed towards the sun as opposed to being sort of dragged back into the rest of the magnetic field? And the second question was, are there vortices or other dynamics in that region, similar to fluid dynamics? I'll take the second question first because it's really interesting. A lot of our field comes out of the field of fluid dynamics. I mean, a lot of the phenomena we see, we first try to understand it from a lens of what would happen if it was a fluid. And the only other thing we have to worry about is the fact that it's a fluid with a magnetic field in it. And so that does give you some different phenomena. But to first order, a lot of it is fluid dynamics. And you do get vortices. You get Kelvin-Helmholtz instabilities, as you'd see when there's a cloudy day, and you kind of get these kind of crested waves that you see over on the edge. Different kinds of instabilities like that, very common. The magnetic field is what drives the cusp to the front. Essentially, there's a magnetic field on the Earth and a magnetic field in the solar wind. And the superposition of those, the sum of those, is what gives you that particular geometry. So when you add them together, just so it turns out that, yeah, if you took just the Earth's field by itself, that would be a dipole field, essentially, that's pointed 11 degrees off the spin axis, and it would just be wherever it is. Different times of the year be pointed towards the sun or away from the sun. But when you put the magnetic field, the solar wind in, which can be this way, sort of all directions, that tends to give you something that's pointed towards the sun when you add them together. Other questions? Yes?
Is there any chance that the rate at which the atmosphere is escaping change over time? I mean, we were assuming that there's a certain rate, and so we have billions of years left. but, you know, are there things that could happen that could change that rate, and has it changed that we know of?
An amazing question. The question is, has the rate of atmospheric escape changed on the Earth? And I guess the first order of the answer is we don't fully know the answer to that question. I know one of the points of the MAVEN mission was to see if they had evidence based on isotopic ratios of how that had changed over time. Try to estimate, was there a loss rate that was different 100 million years ago or a billion years ago? On Earth, because of the kind of static nature that we have such a large gravity and a magnetic field, if we lost the magnetic field, for example, as we do every 100,000 years, so we go through a reversal where the field weakens, I'm not sure what would happen in that case. We probably would get some more atmospheric loss than we have now. On the other hand, those periods are infrequent and far apart. So if you integrate over the total loss, it's probably not that much, but maybe you would get a spike during those periods. Still not enough to threaten us. Obviously, we've had plenty of those reversals, and we've had every 200,000 years for the last 5 billion years, but it's not trivial. And then the other thing is, if the sun were to suddenly change its output, that would be a major problem. Now, we think we understand the sun to first order. We don't expect it to go through large things, but whenever there's a solar flare, to a small extent, we do get an additional burst. So if the sun went to a very, very active, like I'm talking hundreds of times more active than it is now, we would have this issue. And that's why we try to understand exoplanets in that same lens. If that sun is very active or very different than our sun, that could dramatically speed up that process. Yes?
Does human activity have any effect on the loss of the atmosphere?
The question is, does human activity have any effect on the loss of the atmosphere? And the answer is no. These gases are basically, it's this giant reservoir of the atmosphere, and even our pollution and our CO2 and all that stuff, it's not affecting these layers of the atmosphere essentially where we're interacting with solar wind. Yes.
I'm just curious, you don't have light at all. It's 24 hours dark. Now, if you don't have clocks there, you don't know when is what, so when are you hungry? You have lunch,
yeah.
breakfast or dinner or what?
Yeah.
I just wonder what happened before, you have clocks and things like that.
Party all night long.
Yeah. The question was, what do you do when there's no sun and you have no way to set your circadian rhythm? And it's a great question. It's what I was worried about when I went there. And the answer is sort of what this gentleman said. We did party a lot because you it's so dark outside, and so you're either sleeping or you're with people. And one of the things they enforce is there's a central mess hall. People don't cook in their own homes or their own apartments. There's a central mess hall. You go there for every meal, and they want you there for every meal. You're hungry, you're not hungry, you still come and you sit there. And that's really a mental health wellness check, is they want to make sure no one's sitting in their room and being depressed. They have, for example, an alcohol quota that you're not allowed to exceed unless you're drinking wine, which is unlimited, apparently, because the king of Norway likes wine. But they try all these things to try to keep you on a rhythm and try to keep you mentally well, and also talking to your friends and socializing, because it's a danger.
Yeah, and I noticed too that inside the building, you're dressed normally. I mean, it's pretty warm.
Yes. Yeah. The question was, how warm is it? I think it's actually pretty warm there compared to Alaska. When we go to Alaska, it's minus 40 degrees. Here, it's typically around freezing. It's just very windy. It can get cold here, but inside the building is very cozy. You do have to take your shoes off. One of the traditions is to take your shoes off when you come into the building. So that's probably the one concession you make, and you hang up your coat. And
then
yeah.
Also, you're on top, so when you are there, where is north and south?
Yeah. The question is, what about the directions of north and south? We're far enough from the North Pole that it still has meaning. We're not right at the North Pole, so we still have a northerly direction and so on. You don't have the sunrise to tell where east is. So there are some differences, but
yeah. So you can look at the stars too, right?
I'm not an expert in that. But if I was a navigator, I suppose I could do it that way. I look at the mountain and say, okay, there's the mountain with the light on it. That must be that part of town. The town is not that big, so you can't get lost. So, yeah. Any other questions? Yes, Stephanie.
So will you be going back?
We are going back in 2.5 years. We're going to go in the summer. Glenn Collinson, my colleague, is leading a rocket to study a different phenomenon that happens only in the daylight. It's kind of the opposite of this mission. The Norwegian rockets are launching this November, December. I wanted to go, but it's kind of conflicting with the conference we have. But they will be there launching in November 26th to December 9th timeframe.
Have you ever been lucky enough to get it on the first try?
The question was, have we ever got it on the first try? And the answer is, not me. Usually this is actually an easy one. 5 days is pretty easy. Sometimes we've gone two-week periods where you go home and you come back. It has happened, but it's pretty unusual. People are so nervous. Like you put all this work into it. You always think, is that really what I want? And usually the rule is if you see something that's good enough, you go, because you can never predict it. But sometimes you might say, well, I'll wait till it gets a little better. And then, of course, then you wait 2 weeks if that happens. Yeah. Other questions?
Thanks for coming.
Thank you very much. I really appreciate it. Thank you.